So good morning to everyone, and first of all, thank you for registering to follow this webinar. Before starting, I want to thank a lot all Additool partners, and particularly IFM Adimat for helping us organizing this webinar. And to everybody here, I send you all my best wishes for this new year to 2023. To briefly introduce myself, my name is Pierre Diaz, and I am a metal additive manufacturing design engineer on the Adimador platform. Adimador is a technological center dedicated to large-scale metal additive manufacturing with processes such as DED Wire Laser, DED Wire Arc, DED Powder Laser, etc. And where our primary objective, hello, thank you. And where our primary objective is to transfer the skills acquired in the field of metal additive manufacturing and to transfer it to SMEs to increase the level of knowledge of this high value added sector.
No.
If you can cut your microphone, please. Thank you very much. This webinar is a part of Enterex Sudway. Enterex Sudway Additool project, of which I will very briefly explain the input and the output in the following slides. But I will discuss today about some feedbacks or trials we realized on new emerging technology on the market. It is the test of FFF, or fused filament fabrication, or FDM, fused deposition modeling, loaded with metallic powder, so metal charge, or what we can call how to make metallic additive manufacturing accessible to as many people as possible. So Additool is composed with 9 main partners. The technological platform STA Compositador Adimador as a project leader of this project. We are based in Bayonne, in France. We have the Basque Country cluster Adimat, based in San Sebastian, in Spain. We have also the National Agency for the Mold Industry, CEFAMOL, based in Marina Grande, in Portugal. The Technological Center CEIT, based in San Sebastian, in Spain. Also, we have the National Engineering School of Tarbes, ENIT, based in Tarbes, in France, south of France. We have the Advanced Center of Aerospace Technology, FADACATEC, based in Seville, in Spain. IA, based in Leiria, in Portugal. The Technological Center or Platform, LORTEC, based in Ordizia, in Spain. And finally, we have the University of the Basque Country, UPV EHE, based in Bilbao, in Spain. So a big consortium with 9 partners, but also we have 9 associated partners that we can rely on to extend the work area of Additool. And namely, we have the Andalusian Innovation and Development Agency, Agencia IDEA, the cluster Andalusia Aerospace, the Technological, Artistic and Professional School of Pombal, ITAP, the manufacturer and developer of metal parts, Gestamp, in Bilbao, the manufacturer of aeronautical parts and structure, the French mechanical cluster Mécanique Vallée, the Spanish precision machine manufacturer MEUPE, the rubber composites and thermoplastic injection company, which is Somocap in Jatsu in France. And finally, we have the company specializing in railway system, Trenasa, in Navarre. So, as I said, a big consortium. And the objective of the project, Additool is divided in 4 major poles, or 4 main work package, whose the main objective at the end is to promote metal additive manufacturing technologies in the Sudway area. So the Sudway area is the south of France, all the Spain and all the Portugal. So the first work package of this project is the market study. And the market study conditioned the whole of the rest of the project. And this market study has made it possible to have a deep analysis of the tooling market that we realize at the first year of the project. We realize also an opportunity study for the development of MIM technology and a definition of real industrial study cases we developed on the project. And on the Additool website, www.additool.ee, you can find a complete deliverable downloadable for free in a PDF format and available in 3 languages, French, Spanish, and Portuguese. And it's totally free. You can have a check on it. The second main axis of the project was the technological demonstration part. And thanks to the market study we realized before, it was possible to develop new materials, so a new powder for metal additive manufacturing. We characterize the wire and the powder for each technology. So we have a lot of material testings with raw material and also all the specimens after manufacturing. We do some tests on this material. And then we were able to manufacture five pilots and to test in real condition. The test in real condition will be at the end of January until February. And finally, the third and fourth major axis, the last work package, are the training, the formation, and also the mobility and the diffusion or dissemination. So we organize 5 trainings modules for students, about 2 weeks of trainings. We had also a mobility of researchers and PhD through the project. So we exchange a lot of people from each entity, and we can work with other partners. So we create a great collaboration on it. And the last one is training through 7 webinars. So this one is the 5th webinar that we organize. And you can find also on the website all the previous webinars we recorded directly on the project, so on additool.ee. So it was just an overview of Additool, where the webinar it's organized. Going back to the main theme of this webinar about metal charge fused filament fabrication technologies, there is a brief reminder of the technology and the different tips to have a common basis. So the public is large today, so there is a common brief. In this FFF metal charge technology, we will use classical machine with FDM process. And FDM process, it's simple. So it's an additive manufacturing technology. By depositing a polymer filament like this, it's a coil of filament, layer by layer, and melt with a heated nozzle. So the filament is led to the extruder. The extruder uses torque and a pinch system to feed and also to retract the filament with precise amounts. We have a heater block here to melt the filament at the usable temperature. The heated filament is forced out the nozzle with a smaller diameter, and the print head and or the bed can move to correct the X, Y, and Z position for placing the material. Okay, so very simple. And this technology, with this kind of technology, we can find 3 main tips of architecture that can be very interesting. The most common is the Cartesian machine. So the Cartesian machine is the most common. It is precise. We have the X, Y, and Z like this. It's very easy to install, and all the market with consumer aspect have this kind of technology. We have a good ratio between printing speed and also final rendering, but we have some inconvenience like the inertia of the head in the direction of the displacement. that require generally a slower kinematics. The second main tip that we can find also on the market is delta machine. Delta machine is a more rigid structure that allow better jack, better acceleration, and an increasing of the speed because we have low inertia because we are not on the direction of the displacement. Okay, but this have some inconvenience like generally often lower print volume. It is more complex to install and program because we have a delta machine and not a linear axis like this. And finally, the last one is the robotized FDM-R, so fused deposition modeling robotized, which allow to have a very large size. So it's depending the size of the cell. It's multi-axis deposition. We can have a robot like this with 6 axes. We can add a positioner if you want, so to have 8 axes, and you can move on a 3 dimensions. So it's very, very interesting. However, this kind of technology, we can find a lack of precision due to robotic arm, and it's very more complex of programming this kind of technology. Also, before I introduce the metal charge aspect, we have to take into account 2 main types of material distribution, and we will see that it is important for the following. The FDM process is composed with an hot end that we call an hot end with heater zone and a cold zone. Okay, the hot end is important to melt the filament. So the filament is pushing here. We melt it. We have an hot end on the machine. This is an important system. This is the main important system to melt the filament. So as I said, we have a heating block here with the nozzle. We push the filament and we melt it. The filament go through the nozzle with a small diameter. However, we have also a cold zone that is important to refresh the filament before the nozzle to avoid a melting point here, for example, and to have a flexible filament here. So this is the hot end, and the hot end has to move. And we have 2 main types of material distribution. We have the Bowden printing and also the direct drive printing. This is important because with FDM metal charge, it is preferable to have a direct drive system. Just to have a common basis, the Bowden printing, we have the extruder. This is a motor of extrusion of the filament. The motor is attached to the frame of the 3D printer and push the filament into the hot end through a tube. And this tube, we call it the Bowden. The advantage on it to have the extruder deported than the directly on the hot end is we have an higher speed on it because we have less inertia. We don't have the motorization directly on the head, so we have a higher speed. We have low ghosting. The ghosting is the vibration aspect we can have on a part when we are printing an edge, for example. When the part go through the 90 degrees edge, we have a vibration, and we can see directly on the skin of the part. So with this kind of with Bowden printing, we have low ghosting, and we can have also, because we don't have any electronic card or PCB, etc. We can have a higher temperature of the chamber, so we can increase more than 80 degrees, 100 degrees on the temperature chamber. However, the inconvenient, we can push only rigid materials because we will have difficulties to push the filament. If it's soft, for example, we will have some distortion on it. It's not well guided, and it's more difficult for fragile filament or very soft materials. And also, it's difficult to manage some retraction on the filament because we have a lot of length on it. Contrary, we have the direct drive process where the extruder and the hot end form a single element, and we minimize the distance between the pull point and the nozzle. Okay. Advantage, we have a better management on retraction because it's very direct, as a process say, and we can push some technical material. It is possible. And we have generally a better printing quality on it. And convenient because we have a mass embedded, which is bigger. We have a low speed, the head is heavy, and we can have a possible presence of ghosting. And also because we have electronic, the heating chamber is more complex to put, okay, and to protect. So with metal charge, the objective, and it was the objective also of Additool, is to obtain an all-metal part using conventional 3D printing technologies. Okay, so technology we can find directly on the market with Creality, Razer 3D, or Zortrax, or etc. Every machine we can find on the market. And the objective is to make accessible metal additive manufacturing technologies to everyone. As you may know, the other processes like DED wire, DED powder, or PBF laser, the cost of the machine is very, very important. It's more 500,000 euros, 1 million euros for the machine. And we have the idea on Additool to technology which are based on MIM process. It's MIM Like, it's metal injection molding. MIM process we can also compare to binder jetting technology. It's a powder bed with a binder. And we want to compare this technology, this material aspect, etc., to another technology. And then we want to reduce the delivery time and the time to market using this kind of technology. With FDM metal charge, we will use a polymer filament, okay, that will be loaded with a metallic powder. And approximately, the powder inside the filament is about 18 microns, D90, so 90% of the filament are less or equal than 18 microns, so it's very, very thin, the granulometry. And we have a value chain like this. So we have the feedstock here. This is a coil of filament. We print it, okay? We call this part the green part. Then we have to debind it. This is an extraction, a quasi-complete extraction of the polymer, okay, that we call the brown part. And then after the brown part, we have to sinter at normal atmosphere. We have to sinter and to have at the end the final part or the sintered part. Okay, so through a polymer machine, the objective was to create a fully metal part. Okay, so in the theory, it's a little bit magic that we call like this. On the market, we can find some new filaments. It does not exist a lot of suppliers, but if you take a look on internet, you can find the BASF with an ultrafuse 316L stainless steel and 74 pH. That will use catalytic debinding. I will explain you just after what's the difference with a thermal debinding and another. So BASF with catalytic debinding. We have also Nanoe with the new Zetamix 316L and Zetamix H13 with thermal debinding. This is the material we have took for the test. We have also Nanovia that are developing a new MT316L with thermal debinding. And we want to compare this kind of filament. Filament for accessible for classic machines, so open machines that we can modify parameters, etc., and that we can play with this, and compare to the reference of the market with the Marforged Metal X system. The Marforged Metal X system developed a lot of materials at 74 pH, base copper, Inconel, H13, ADMD steel, etc. But all these materials are dedicated to the Metal X machine, and it's proprietary, so you cannot modify parameter, you cannot play with the machine to optimize it. And the debinding is made with a washer, and inside you have Opteon 79. I will explain just after. After printing, you have the thermal treatment to do, because it's not enough to print. At the end of the machine, you have a mix between polymers and metal part, but you don't have any properties on it. And you have to debind it. And the debinding is the key operation of the process. This is the thing you have to master in priority, and it's a real job to master debinding. And the debinding consists to remove the organic binders from the feedstock once the part has been printed. So the quality of this operation is very fundamental. Okay. And all the fissuration, the cracking, all the damage on the part at the end of the oven, when you open the oven, is due generally to a bad debinding. Okay, a very large defect which appear after sintering are generated with an adequate debinding. In the majority of cases, we have two separate debinding in the process. Okay, so we have the first debinding. The first debinding will open a little channels, okay, from the earth of the part to its periphery to help the second debinding to remove all the binder inside the part. And for the first debinding, we have three main types of debinding. We have the catalytic with the BASF patent and the Catamount process that I explained just before. Catalytic debinding, we have the binder, it's polyacetal, attacked with nitrogen and nitric acid. Okay, so we turn it into gas and we burn out of the oven. Okay. Catalytic debinding, it works. We have good results on it. However, you need a lot of authorization in your laboratory. So in the company, it's difficult to have nitrogen or nitric acid. That's why in Additool, we don't want to make it accessible to large SMEs. We don't want to use any nitrogen or nitric acid. Okay. The second type of debind is the debinding in water or in a solvent. That is, it is the technology of Marforged, for example, with the solvent is Opteon. The binder is dissolved, but not fully. In the first debinding, we don't debind fully the part, but it's just to allow the part to be manipulated. Okay, so we debind a little bit, about 50%, more or less. We create channels, and so then we can have a thermal debinding after. And then for the first debinding, the last tip is to have a complete thermal debinding. And thermal debinding, the binder is vaporized by increasing the temperature very softly to avoid cracking and damage on the part or deformation. So it's important to note that this is the slowest technique and consume quite a bit of energy, and therefore it's not very productive, okay? And consume a lot of gas also. And then we have the second debinding, and the second debinding for every process is almost always thermals. And the objective is to eliminate all the rest of the organic binder. So it is possible advantageous to have the second debinding in the same oven and in the same cycle as the sintering to reduce handling, energy losses, and avoid the oxidation. It can occur when we open the oven. Okay, so we advise to do it on the same oven. However, you can have also a little bit of contamination during the first debinding or second debinding and the sintering. You have a lot of polymer that is vaporized, and you can have contamination on your oven. So it's important to note also. On this picture, just below, you can find some example of debinding problems that occur very frequently. The first one is a bubble like this. So generally, it's a debinding very fast, and the polymer explode a little bit and cannot extract quite good out of the part. So you have some inclusion like this, some bubble, and inside there is nothing. There is only gas. So not a fully metal part. You can have also cracking or fissuration like this, and porosities that we can find on different problem of debinding. Also, you can find on this picture some example of debinding and sintering systems. This is a pre-debinding oven, an oven of sintering, and what we see here is the oven is cylindrical. This is very important for a sintering part, because in Adimadour we don't have this such oven. We have the same oven, but in a cubic format, and the cubic format is not adequate for sintering. So the sintering have to be in a cylindrical oven like this. And at the right on the picture, you can find the system, the equipment of Marforged with a washer to debind with a solvent, with Opteon, and then the sintering oven, which is also cylindrical. Okay. And then at the last step, we have the sintering. So once the debinding step is complete, the part must be consolidated with a sintering step. So it's a thermal process, and with when we heat compacted powders, it's important to do below the melting point, and the sintering gives them the cohesion after cooling to obtain the desired microstructure of the final material. So we have a raise of temperature, a maintain, and then a decreasing. Important things is when we raise the temperature for the sintering, all the polymer we dilate will cause a lot of retraction of the part. So the part will be reduced after the sintering. So we have to master exactly the proportionality between the programming, the manufacturing, and then the final geometry we will have after the sintering. It's around between 19 to 20, 26, 25% of retraction, and it's different between the X, the Y, and the zeta. So that's why I explained a little bit before. So the part after debinding, we have the grains of metals. Step one, we increase the temperature. We start to weld to each other. We reduce the porosity. Step two, the same, and finally we have the sinter part with some close porosity because we sinter in atmospheric pressure. We don't have any pushing on the sintering. Instead of classic sintering of powder with force outside, with 3D print machine, you will have a lot of different geometries, and you will have it's not possible to have a pressure in the sintering. We can have the heap that we have tested. I will explain before, but you cannot have a mechanical force external because you have a lot of different geometries. Okay. Here you can find some examples that you can find on the market. So part after sintering and with different geometries, different complexities, and it works. If someone can do it, it's possible, and we can find directly on commercially market. However, that we kind analyze it is that the parts are little and are flat. If you can take, you have the plate, and it's not so high. Okay, so it's little part, and the thickness are equal. If you take a look on it, the three parts, the thickness of each walls are equals. So it's it is easy to debind when you have equal thickness on different walls. So it works for little parts. And to do it, also, we have to respect the curve that the supplier gives us to do the debinding and the sintering. For example, in Nanovia, you have a curve. It depends also the polymer you have. It depends the different metal. The 316, the temperature of sintering is different than the H13 at more than 1,400. And also the time is different. For example, in Nanoe Zetamix H13, the time of the debinding is around 91 hours. And debinding and sintering is about 91 hours. So it's complicated for an SMEs to launch a heat treatment on the Monday and to have the part on the Friday after. Okay, but you have some rules, some curves you have to follow to print the material and to have a final part after. In the Additool project, when we see this kind of technology, we say, okay, it's very, very interesting, and we want to test it. So we called Somocap. It's an associate partner of Additool, and they give us a kind of part. It's originally it's a part of injection mold, and at the original part you have only a simple hole for cooling the polymer part all around. And the objective of the project is to do some conformal cooling, okay, to increase a lot the performance of the cooling system and the cooling polymer all around the injection. And the objective is to manufacture this part with FDM metal charge technology and to sinter, to compare with and without heap, hot isostatic pressing, to machine the part to respect the dimension, increase the performance of this tool by adding a cooling channel inside, as I said, and we will compare two different technologies. So we will compare the reference, the Markforged, and comparison with the Nanoe H13 available on the market, and that offer a possibility to be mounted on every classical machines. And then we have to compare the properties between the original machine part, the H13 with Markforged, or the 74 pH with Markforged, and also with Nanoe. before doing it, we have to respect a lot of recommendation in terms of design rules that I will explain just after, but also some guidelines for the extrusion. As I said before, is why I made a little reminder. Given the fragility of the filament, it is loaded by more than 50%. So you have 50% polymer and 50% metal powder in terms of volume. Is about 90% in terms of mass of metallic powder, but 50% in volume. A direct drive machine is recommended because the filament is very fragile. Also, the nozzle have to be at 0.6 millimeter minimum of the diameter to prevent it becoming clogged. Okay. In Additool with our machine, a Langster, we took 0.8 millimeter. It's better, and we have more fluidity directly on the filament. Also, due to the abrasiveness of the filament, the nozzle that what we see it have to be reinforced. So as steel, at least on steel, but it's preferable to have some treatment on ruby or ceramic directly on the nozzle to avoid an increasing of the diameter at the end of the manufacturing. Also, with this kind of filament, and it's different for only polymers, we want to avoid every space on the interbead. Okay, so on the interbead bond, to avoid holes and after debinding sintering, we have to over extrude. We have to put an extra extrusion about 10% or 15%. Okay, well, it's depending on the nozzle and the material you're using, but you have to over extrude a little bit. Okay, so the filament being fragile, the extruder will be fitted with very low rotan spring. It's that we see it with a classical extruder. When we push the extruder like this, the material is very fragile. It's like a little bit like butter. Yeah, we grind the filament very easy. So we don't have, it's not necessary to have a big force to push the filament. And we have to avoid any retract of the filament. So we push only the filament. We don't have any retraction on the filament. Okay, so we have to avoid it as much as possible. Also, that is something good. We have some supplier guidelines. Each material is different, and we have different polymers and different metals. The charge rate also is different. And don't hesitate to take a look on it. For example, you have the condition for debinding, the time, the ramp of increasing temperature. And we have also the oversize factor in X and Y direction. We have 22.3%. And on the Z direction, you have only 20%. So it's different. Okay, so don't hesitate to take a look on it. And also, some design rules for 3D printing. Due to post-printing treatment, as I said before, you will have a decreasing of the geometry. So you have to master it precisely. So my advice is to create the part on CAD format in the good dimension, and then on your program system like Simplify 3D, Cura, etc. You have to put another scale directly on it on X, Y, and Z. Okay. So you will have a maximum part size. Important tricks also. The maximum size is not depending on your machine of printing, but it is depending on your debinding and sintering furnace. This is very important because if your machine can print 500 millimeters and your oven only 100, the maximum size will be 100. Okay, and it's very complicated on the market to find sinter and debinder oven more than 100 millimeter of diameter. So that condition your maximum size. and the minimum, it's about 7 millimeters. So I can pass very briefly. Minimum wall thickness is about 1 millimeter, or the thickness of 1 or 2 well bead. You have also, like a classical machine, an unsupported overhang. For the printing is 35 degrees mini. However, for the debinding, 35 degrees, you will have support to avoid collapse or deformation during your debind process. Okay, so support is necessary to debind and to sinter. Maximum solid wall thickness, and this rule is very important, but it is only for the thermal debinding, the process that requires only thermal debinding. It is not possible to have a thermal debinding of a big wall about 20 millimeter of thickness, because you will not debind from the earth to the periphery. You will have a lot of deformation, a lot of collapse, etc. So if you are, it is important to not go after 5 or 6 millimeter for thermal debinding. If you are a catalytic or in a solvent debinding before, you have no limitation on the size of the wall. And 3 millimeter of the pin diameter, just for information. Something important also is beware of critical angles. So yeah, it's true for every process, like machining, like metal additive manufacturing. Yeah, prefer to take some transfers of some curve in the edge to avoid abrupt change of size. And also, don't hesitate to put some stiffens like this to avoid a twist part. Sorry, after debinding and sintering. So in Additool, we test in a Dimado a lot of parameters. So parameter identification with a 0.8 millimeter nozzle, with the Langster S600D we have in our space, with a direct drive head, and we print a lot of specimen. So about to see exactly if we can print every data, etc. Some pins, some traction specimen, etc. To test also coding channels, traction, etc. etc. So we print a lot of this kind of specimen, and we test also several tests of debinding and sintering, but with the furnace we have in our space, and it's a cubic oven with a porous wall inside. And the debinding, we have done it with a mixture of gas. It's argon and 2.5% of hydrogen to avoid oxidation and to remove correctly the binder. Okay. So Nanoe require 91 hours of debinding and sintering, and this is the better way with our cubic oven. This is the better part we did, because the oven is not adequate, and we have still some bubbles, like I showed you before. We have still some polymer contamination, etc., etc. And we judge that that 91 hours of debinding and sintering is not great for SMEs, is not viable for the industry. So we have to reduce it. Yeah, some picture about the test. We see the bot here, and the bot doesn't exist anymore. We have a lot of collapse, a lot of bubbles. We have deformation, cracking. So every damage we can have, we add on this kind of oven and this kind of filament. So because we are not able with this cubic oven to perform it, we call Nanoe. This is a supplier of the filament, and we print several samples like this. Is about 20 millimeter of height and only 15 millimeter of diameter. And with the supplier also, with this kind of little part, we have still deformation and little collapse, the presence of blister, bubbles, etc. So it's not so, yeah, this kind of filament yet with the curves that the supplier gives us, etc. doesn't work as we want and as we as we want. So we have a too long debinding and sintering cycle. We have very poor mechanical properties and very high consumption of gas, about 1.6 liter per minute. And with the complete cycle is about one gas cylinder of 50 liters at 200 bars. And we have a poor distribution of gas in the cubic oven. So we call for help to SEIT, one partners of Additool, and they are experts on this kind of job, sintering, debinding, etc. It's their job. So we have printed a lot of samples to optimize this kind of process. So as I said, it was some specimens. So yeah, 15 millimeters of diameter and 20 millimeter high. You have the composition of the H13. Yeah, remember just it's about 0.4% of carbon. And the objective of the SEIT is to optimize exactly the debind and the sinter to do something with this kind of filament. And after several trials, they want to perform a chemical debinding just before, about 5 hours at 50 degrees, with an immersion of the part in alcohol isopropanol. Okay, it's a classical alcohol we can that everyone can have in the company. Then they optimize the curve of the thermal debinding, and we see here that we have only 10 hours of debinding and also sintering. And they perform also a heap to close porosity. We will see just after. So with the expertise of SEIT, we will reduce about 91 hours of debinding and sintering to 17 hours that could be interesting for the industry. To do it, they perform some thermogravimetric analysis, so we can see two steps for debinding without chemical, with chemical, etc. And they adapt exactly the curve to find the good temperature and the best way to debind. So before we have something like this, and with the new thermal debinding, we have something like this. So it's better, and it's allowed to eliminate the cracks and the trap bubbles from the H13 samples. If you can compare, it was before, and with sinter optimization, with sinter we have something that can be very interesting, something interesting. But if we take a look on, we have performed some tomography in UPV and also in the FADACA-TEC at controlling atmosphere and temperature. The sintering is successful, but we have a problem according the periphery on the part. We have still some porosities, but this is due to the difference between the strategy of manufacturing, because you have a contouring perimeter outside and the infill. And so we have to retake the parametry to oversee exactly the overlap between infill and perimeter, but we have still some internal porosity due to the process. So we have suppress. No, it doesn't matter. Yeah. However, yeah, as I said, the Marforge has a very good result. This is a reference. All the samples are very straight. You don't have you have some porosity, but about 2.3 or less than 5% of porosity. This is the reference. And inside, by Fadaka Tech and UPV, they have performed some tomography. So 3 samples have been inspected, and we see a lot of porosities inside. So the thermal debinding was not so good with the result of Nanoe. And before HIP, we have only 85. Not so easy to print. Have a little bit of clogging of the nozzle on one layer. You have some deformation, etc. So you have a lot of porosity inside, and the mechanical properties are very poor. Contrary to the Marforged, 5 samples have been inspected by tomography and inspected before HIP, and we have 95% of density. So we have still some porosities inside, but the density is quite good, and we are about the same densities and the binder jetting technologies. And after HIP, so hot isostatic pressing, so at more than 1150 degrees and 150 MPa of pressure, most of the internal pores are closed, as well as the Nanoe filament, as well as the Marforge. So this is something that can replace a mechanical force for the sintering. You can have access to a HIP. But in terms of price, it's very expensive, and I am not sure. It's my opinion, but I am not sure that every SMEs will perform a HIP with each part you will manufacture. So we abort the Nanoe filament because it's not possible. This is only little specimen, but the part we have to manufacture, like this, the part of SOMOCAP, is about 200 millimeter of length. And if you take a look on it, this is a manufacturing by Lortec with Marforge Metallics. The manufacturing, even if the part was cylindrical, has not been made vertically. The manufacturing was only horizontally, okay? Because during the debinding and the sintering process, the oven is still, the dimensions are not enough to place this kind of part vertically on the oven. So they print horizontally, and then they can push it on the oven horizontally. And you see also some support to avoid collapsing or deformation on the geometry with this such big dimension part. And inside, this is a cutting. You have all the cooling channel near the periphery. So this is a part manufactured by Marforge with filament. And also, we have seen on the market a company which the name is Rapidia. It's Canadian, so it's the American continent, and they are developing a new technology. It's not with filament, but it is with aquapast deposition. It is something very interesting that can be the next future, because with the filament you are blocked with a charge, with the printing. You cannot to have a solid filament that you are able to print. You cannot go after 50% of metal charge. With the aquapast, you can have a lot of charge without any defect. So it's an aqua gel, aquapast liquid, But this is the same technology that you are pushing the aqua paste and you are depositing filament. Okay, so the printing is like FDM process, but you can have more than 80% or 90% of metal powder inside. But to do it is not so easy because the dimensions are very big, and it took about 6 months to have a such part. I have it with me. I receive it on Tuesday this week. So we have to machine it. We have to perform some tests. We will make some tests with the walls. With the wall we are here, specimen where we can machine some traction and specimen directly inside. And then we will test this part on a real condition at Somoka production line. So to conclude, it's debinding and sintering process have been optimized for NanoWire 13 thanks to SEIT, obtaining good external geometry and control sea level. However, we have still some heterogeneities in the printing process that can have some difficulties to obtain the successful demonstrator. Something interesting also is that the HIP, orthostatic pressing cycle, allow to close most of the porosity in the NanoWire H13 and also with the Marforged. Marforged H13, it's almost dense already after the sintering, and with HIP we have 100% of density, so very interesting. But we have analyzed that it is necessary to have the first chemical debinding to open pores and facilitate the thermal debinding, and to have also a cylindrical oven, not cubic. Okay, so chemical debinding is very necessary to open channels and to reduce a lot the time of debinding and sintering. It works. This kind of technology works for parts with little dimension, so less than 100 millimeter. But we have a lot of limitation with the oven and difficulty if it is more than 100 millimeter high. It is necessary also to master perfectly the value chain if you are using an open system, and to debind and sinter, it's a real job. On the market, we can find, and we have seen on the Formnext this year, that a lot of partnership are created. A company that masters the printing, a company that masters the debinding, and company that master on the sintering. This is the case also for BASF. BASF, their economical model is that you print the part, you send them with the coupons, and every week they are performing post-treatment, and they send you again the part. So in 1 week and 1 week and a half, if you print the part, you can have a metal part after your classical machine. And then we think that yet at this moment in January 2023, it's still too much expensive to be accessible for SME. The cost of the Marforged is around 2,500,000 euros, but you can have some subcontracting that could be very interesting, and yet we think that it's not really ready. But in the following months or in the next year, I think a lot of stakeholders we go in the market, and it will be more reliable and maybe more accessible. So I think there is some hope on this technology. Just for information, you have some idea of the cost of raw material. Nanovia is about 200.5 euro per kilo. Nano is a little bit expensive, is 500 euros per kilo. And yeah, BASF 100 and the Marforged is it's less expensive, but you need to have the complete system. So the metallics, the washer, the sinter, and the material proprietary. Just before stopping the webinar, I want to take 1 minute to speak about the final conference we will organize at San Sebastian. It is the 9th of February 2023, so the next 9th of February. It is totally free, but the registration is mandatory. You can register directly on the website, so additool.eu. The objective of this conference is to transfer the Additool results we have. This is only one pilot we had on Additool, but we performed 5 different pilots. And then we will have some external speaker like IM Power that will speak about sustainability of MIM. We will have AddUp, a French company dedicated to DED technology, according to opportunities for the tooling industry. We will have Crownfield for the development into WAM, AddAxis, new software multi-axis programming with for robotics and dedicated to additive manufacturing. And then we will have Rescol. We'll speak about the cold spray technology and in its industrial application. So it's free. Don't hesitate to register. And we are at the end of the webinar. I hope you enjoy it and you have learned at least one thing. And I am at your disposal. If you have any question, I will be happy to answer you. Thank you. Thank you very much. According to the TRL, not industrial. So for it depends the technology. For the Marforged, the TRL could be industrial. The TRL could be around 8, maybe 8 or 9, même with the Marforged. With the Rapidia also, with Aquapast, we are very near TRL 9. But with classical machines that we want to improve with the Additool project, it's about 4 and 5 for the moment, and it's necessary to master, as I said, all the value chain, and you need also some equipment. A classical machine of printing is about 200 euros or 1,000 euros. But if you want to equip your workshop with a debinding system and sintering system, it's about 100,000 euros. So you can have some Chinese oven at 10,000. But if you want something very sensitive and very performing, it's about 100,000. But this is only my opinion. But it is thanks to project like this and that new supplier. So yeah, Nanoe, Nanovia, BASF, etc. They are the first supplier. So yeah, they want to master it. It is very interesting that some kind of this supplier do this job in amount that we can have a reliability system in the next few years, I think. So I hope everything was clear for you. So I wish you again a very nice New Year, a very happy New Year, and then we can discuss in presential at the conference, I hope. So I think we will stop this webinar. Thank you again very much for your registration and for having participated to this little bit long. I hope it was not too long. If you are interested in final polishing, post-processing, do not hesitate to contact. Yeah, it could be very interesting. Okay, Rosler, I not it. Thank you very much. Something interesting also with this kind of technology with you can polish directly the part when you print it. You have some polymers and metal, and you can polish it by hand. Okay, so you can have a better aspect than, for example, DED process like WAM or VLAM. You can polish it, and at the sintering you will have a better surface condition. I don't know if you can see. This is not polished, and this is something polished, and you have a better surface condition. But for the functional surface, it's still necessary to have a good machining with a good surface condition. So thank you very much. I will stop it, and have a good end of week and a good weekend. Thank you, everyone.